Alright, hello everyone again. So here's another problem. So for the given circuit, it says find an expression for the voltage across the capacitor as a function of time. That's what it is. For the given circuit shown, right, VC as a function of time. How the voltage across the capacitor changes over time, or discharges. It's a discharging problem, right? Because it says at time t is equal to 0 in the wing, right? Time t is equal to 0. This battery is disconnected, right? And then but it says, the problem says this battery was connected here for long enough time so that this capacitor was fully charged. So when the capacitor is fully charged initially, before you disconnect the circuit, disconnect the switch, the capacitor was fully charged. So when the capacitor is fully charged, it works as an open circuit, right? It doesn't conduct at all. It doesn't. The current through the capacitor is 0 once it is fully charged. So let's first find the initial condition, right? So we assume that at t is equal to 0, the capacitor is fully charged. Capacitor acts as an open circuit. Why? Because it's fully charged, right? Because it's fully charged, it doesn't conduct once it is fully charged, right? So then we can draw an equivalent circuit to find VC at t is, because this is the initial condition. We're going to need to find the unknown constant once you solve the differential equation, right? So and then at t is equal to 0, let's find the equivalent circuit. So this is going to be your 7 kilo ohm. So when battery is disconnected, so this is going to be like this, right? And this is also this 2, because 6 kilo ohm you can combine as 6 kilo ohm, and the capacitor works as an open circuit. So you have this, you have that, and you have this. And you have the battery connected here. This is at t0, right before the switch is disconnected, right? We want to know what is the voltage across the capacitor. This is VC, right? Because that's the initial condition we need to know. So this becomes 5 plus 2, 7 kilo ohms, right? And that is 1 kilo ohm, and this is 6 kilo ohm, and this is 2 plus 4, 6 kilo ohm. Okay. Now somehow we have to figure out this voltage, and then you can just use Kirchhoff's laws, right? You can simply use Kirchhoff's law to solve this. This is just using nodal analysis. So this is at 1 voltage. It says 1 voltage, right? And so this is our, let's say, reference node. So this is, let's say, V of C, voltage across the capacitor. That's what we're finding. And this is at 1 volt, right? So you can say at VC, let's say this is the currents going, right? At VC, you can say at VC, so 1 minus VC over, right, this current gets divided into this and this, right? So this I'm going to call I1, I2, I3, right? So let me do it from the very beginning. So I1 is equal to I2 plus I3, I can say, right? So I1 is 1 minus whatever voltage, this voltage, that's what we're finding, divided by 1 kilo ohm, right? 1000 is equal to I2 is VC divided by 6,000, 6 kilo ohm. I3 is VC divided by again 6,000, right? So then you solve, right? Solve it. You have only one unknown variable. Solve for VC, and then you will see, after simplifying, you will see 0.75 volts. So that's the capacitor voltage, right? So you can say at T is equal to 0, right? Or you can say 0 minus, 0 plus, just right before you disconnect the switch or right after disconnect the circuit, so the battery, the voltage across the capacitor was 0.75 volts, right? Because we're going to need this condition later. Now back to the main problem. Now at T0 it is disconnected, this battery is isolated, then the capacitor whose initial voltage was 0.75 will start decaying, right, through these resistors, network of resistors. So now that's what we're going to find. Now next problem is, now our main problem is, once this battery is isolated, what would be your equivalent circuit, right? So let's draw the equivalent circuit. So your equivalent circuit, once the battery is disconnected, is something like that. So you have 6 kilo ohm, you have this capacitor, charged to 0.75 volt, and you have this, right? So these are 6 kilo ohm, this is the VC voltage across the capacitor, that will decay now. This 6 kilo ohm, 1 kilo ohm, this is 7 kilo ohm total, right? So I can still do some equivalent. So this 7 kilo ohm and this are, I can just make it 8 kilo ohm. I can just bring this here and put in parallel. And finally, you can solve for VC and solve the differential equation, right? So let's say these are the current, let's say, right? So you can choose any direction. So I1, this is I of C, I2, I3. So at this node, right, we can apply, this is, let's say, VC. At V of C, your KC or Kirchhoff's current law becomes, so I1 plus IC plus I2 plus I3 is all equal to 0 because all leaving the junction. So I1 is, so VC over 6 kilo ohm. I'm just gonna keep everything in kilo ohm. IC, right, which is the current through the capacitor, is C dV over dt. I2 is VC over 6 kilo ohm plus I3 is again VC over 8 kilo ohm, right? Okay, now you simplify this, you simplify that everything, and then where C is this, the capacitance is 1 microfarad. Capacitance is 1 microfarad, right? So change everything and simplify, and you will end up with this. So I have this dVC over dt plus 458 VC is equal to 0. So you'll get a first order homogeneous equation whose solution is, we know, whose solution is VC over, as a function of time, is some A over alpha plus some unknown constant E alpha t, right? But this is your A, this is your alpha, right? So VCT is, this is 0 plus K E minus alpha is 458, and it has to do with the time constant, right? And we know now finding, so to find K, use the initial condition. And what was the initial condition? Initial condition was at T is equal to 0, the voltage across the capacitor was, if you go back in the beginning, that's the reason we found this in the very first place, right? Use that. So at T0, 0.75 is KE0, so it's K. So K is 0.75, right? And now our general solution is, this is how the voltage across the capacitor gets discharged. 0.75 because K is this, E negative 458 T. And now, what is the time constant of the circuit? Time constant, this tau, is just 1 over 458 if you compare this with T over tau, right? And that's going to be 2.18 in milliseconds, right? That's it. So your very final general equation is this, T over 2.18 millisecond. So this is how the voltage across the capacitor decay over time, right? So if you just graph it, it will be something like that. Initially it was 0.75 volt, and then it will discharge like this, right? So something like that.